Hey, what's up, and welcome back to Wind Chemistry. Today we're going to study valence shell electron pair repulsion, VSEPR, or VSEPR for short. It's a study of how covalent compounds form geometrical shapes because of how the electron pairs repel each other. So as you know, electrons have negative charges, so when they get in close contact with each other, they tend to repel, and in the process of doing so, these covalent compounds form these geometric shapes. So the biggest idea that we're trying to get across here is the shared electron pairs repel to be as far apart as possible. So there's a couple things I could do on this thing. I could show the molecular geometry. I can add more bonds like I'm doing here. Okay, and now it shows me the shape, which is linear, and I can also show the bond angles by checking that box. So you don't really have to memorize the bond angles. Okay, in this case it's 180 degrees. But it helps you understand this topic a lot better. Okay, so these electron pairs are repelling each other to be 180 degrees apart. If I throw on a third pair, there's less room for them to work with, so now they repel to form a trigonal planar shape where the bond angles are 120. If I throw on a fourth bond, we are now down to 109.5 degrees, and now the shape is different. It's called tetrahedral. And I will rotate it so you can see how it's geometrical, it's symmetrical, right, on all ends. It's perfectly symmetrical. So they form these shapes naturally. And again, it's caused by the electron pairs repelling each other. And there's so many different combinations, right? If I take away that fourth bond and we're back down to 3 bonds, well, now it's like the molecule realizes, like, hey, we have more room to work with, so now everyone gets a bigger share of the pie, right? So if I throw on a lone pair, okay, it starts to squeeze it again. This is now a different shape. It's called trigonal pyramid. I'll show you all the details in just a moment. But the idea is the electron pairs will cause each other to bend and squeeze so that the bond angles are appropriate. If I throw on the lone pair again, okay, see how it squeezes it? Okay, we went from trigonal planar to now trigonal pyramid. So those are different shapes, right? Take away the lone pair, throw on a bond instead, and now this is known as tetrahedral. So there are small little differences between tetrahedral and trigonal pyramid, all of which we'll explain. What if I double bond? Okay, this is still linear, so this would be like CO2, for example, carbon dioxide. If I triple bond, it's still linear. Right, so the electron pairs, even though now there's 3 pairs here, and they repel to be as far away apart as possible. So the first shape we want to talk about is linear with no center. So for example, things like hydrogen, oxygen, and nitrogen, H2O2, N2, HF, hydrofluoric acid, and HCl, hydrochloric acid, these would be things where they have no center like we discussed in the Lewis dot structures. So again, it was just 2 atoms sitting next to each other side by side. You can't have a middle or a center. So by default, the shape for this thing is known as linear. It's just straight across, right? So this could be an H2 where they're both hydrogens. It's both the same atom. It could be an HF where it's a hydrogen and a fluorine, which are bonded together. But in both cases, they're going to form a linear shape. So here's carbon dioxide, and even though it has the double bonds, again, you just really count what's around the center. And since we determined from the Lewis dot structure that carbon should be in the middle, we see that the carbon is bonded to 2 atoms, and carbon has no lone pairs on it. It's got bonded pairs, but not the lone pairs. There's no like dots on carbon. So again, it falls into this pattern where it has 2 bonded atoms, 0 lone pairs, making it a linear VSEPR shape. The third shape that we want to discuss is something called trigonal planar. And an example would be aluminum chloride, where you have Al in the middle, and it's surrounded by 3 chlorines. And this one has 3 bonded atoms, but no lone pairs around aluminum. Okay, so the thing about aluminum, remember, is it's an exception to the octet rule, where it needs just 6 electrons to be stable. And as I'm pivoting this thing, you would see that the shape is in a plane. So all 3 bonds are in a straight plane, right? So this is like flat, like on a surface. That's why it's called trigonal planar, and the bond angles are 120 degrees apart. This shape here is called a tetrahedral, so it's got 4 bonded atoms and no lone pairs around the center. The bond angles are 109.5 degrees, and examples would be like CH4 or carbon tetrachloride, carbon tetrahydride. This one here is methane. And you would see that the 12 o'clock, the center, and the 5 o'clock here are all in the same plane. There's an atom that's sticking out towards you, and then there's an atom going back behind your monitor. And if I rotate it, again, the same pattern occurs. So 3 of them are in the same plane, the 12 o'clock, the purple one in the center, and then the 5 o'clock. Those are all in the same plane. There's one sticking out off the plane of your monitor, and there's one going back. Okay, and again, I can rotate it a different time or a different way, and 3 of them are in the same plane. One of them is sticking towards you, one of them is going back. So that is a tetrahedral shape. And what's cool about this is when you draw the Lewis dot structure, you would assume that the bond angles are actually 90 degrees, like they're just perfect right angles. So the Lewis dot structure does not show the true 3-dimensional shape, because again, the Lewis dot structure is just a 2D model, right? So it's flat on your paper, so you wouldn't know what the bond angles are. So when you put this thing all together, you would see that the bond angles are actually bigger than 90 degrees. It's actually 109.5, and that's how the 4 corners of the 4 atoms are arranged. So this shape here is called trigonal pyramid, which has 3 bonded atoms and 1 lone pair, and this is not to be confused with trigonal planar. So as you can see, I'm rotating through. We have 3 bonded atoms and 1 lone pair, and the bond angle is 109.5. Okay, so this would be like phosphorus trihydride, which falls in this pattern. Now if I take away the lone pair, it becomes a plane. Okay, if I add in the lone pair, this is still a trigonal pyramid, because you can see the base looks like a pyramid. Take away the lone pair, look at the geometry, it says trigonal planar. So these 3 bonded atoms are in the same plane. But if once you throw in the lone pair again, it becomes trigonal pyramid. So those are the slight differences between trigonal planar and this one is trigonal pyramid. So once again, I'll build the shape. That's trigonal planar. See how they're all in the same plane? This one here is trigonal pyramid. And trigonal pyramid has 3 bonded atoms and 1 lone pair. So this last shape that I want you to learn is called bent. So you can have 2 bonded atoms and either 1 lone pair around the center or 2 lone pairs. So this would make it a bent shape. So an example would be like water, which is the one I'm showing now. It has 2 bonded atoms around the oxygen, and then oxygen has 2 lone pairs, kind of like Mickey Mouse ears. Now if I take away one of the lone pairs, it's still a bent shape. If I add on that second lone pair, it's still bent. It's just the bond angles are now slightly different. So you can have water, which is a 2-2 bent, so that means 2 bonded atoms, 2 lone pairs. Or you can have something like nitrite, which is a 2-1 bent, so 2 bonded atoms, 1 lone pair. So I've barely scratched the surface with all the VSEPR shapes. Okay, so these aren't really included in my notes, it's more of an FYI, but you can have stuff like trigonal bipyramid, which is 5-0. Octahedral would be 6 bonded atoms, no lone pairs. You can have a seesaw, which is 5-1 or 4-1 in this case. Okay, what about a 4-2? This would make it a square planar. So you can test for yourself, what the other combinations might be. Like there's so many that we haven't really looked at. I'm just giving you just the 5 or 6 basic shapes, but you can test like a 2-3, a 3-2, 4 bonded atoms, 1 lone pair. How about 3 bonded atoms, 3 lone pairs? And will double and triple bonds make a difference? Okay, so you can have all these different shapes here. Once again, that's a 6-0 octahedral. You can take away some of the bonded atoms, substitute that with a lone pair. So this one is a 4-1 seesaw. You can have square planar, right? So there's so many different shapes that I haven't really discussed, but just know the ones that are in the chart that I mapped out for you and that we explained earlier. This one's optional to learn. Okay, these are more complex VSEPR shapes, and maybe you'll take this again in college where they expect you to understand these VSEPR shapes here.